In this video, we are going to discuss about two processes, isothermal and adiabatic. I have mentioned these two words in the previous video. What is an isothermal process? What is a adiabatic process? Difference between the two and some problems relating to these two processes. So first, we are going to deal with the isothermal process. As the word isotherm means it is a constant temperature, a process in which the temperature of a system remains constant, a process in which temperature remains constant. So it's called isothermal process. A process in which the temperature remains constant is called isothermal process. Now, change in volume and pressure in isothermal processes are called isothermal changes. As temperature is constant, I've already told you there are three parameters: pressure, volume, temperature, and the fourth one is mass. Obviously, because the variant mass is not changed, or the parameter mass is not changed anywhere for a fixed mass of gas. If the temperature is constant, then the other two parameters are known as the isothermal change. If we have any change, if we do any change in those two parameters, that is volume and pressure, according to the isothermal process, those should be called isothermal changes. So I can write the changes in volume and pressure, changes in volume and pressure in isothermal process are called isothermal changes. They are known as isothermal changes. Now we have to understand two things. One is isothermal expansion and the second one is the isothermal compression. Now we all know what is an expansion or is a compression. So in accordance to the word isothermal, we will discuss what is an isothermal expansion. Now we take a gas enclosed in a metallic cylinder, piston arrangement, metallic cylinder piston arrangement. Suppose a gas is enclosed here. The cylinder and piston are made of conducting material. These are made of conducting material. Both the body of the cylinder and the piston are made up of conducting material. Now the piston can move without friction along the inner walls of the cylinder. That means no energy is expended in overcoming frictional force. Now if the gas expands very slowly, an external work is done. I repeat, if a gas expands very slowly, an external work is done by the gas. So if this piston has to move upwards, the gas enclosed will have to do work. Now if the gas enclosed does work, that means energy is expended by the gas or work is done by the gas. So expansion means piston is going to move upwards. That means gas is expanding. Gas is expanding and doing an external work, that is moving the piston upwards. Now, how is the gas doing the work? Because we all know that we need energy to do work. So from where is the gas getting the energy from to do work? Gas is getting the energy from its own stored internal energy. So if it does work, so the internal energy will fall, because if internal energy is expended, so internal energy level of the gas will tend to fall. But the internal energy of a gas indirectly depends on the temperature, or rather directly depends on the temperature. So temperature of the gas will also fall. As the internal energy falls and internal energy is proportional to temperature, so temperature is also going to fall. Now, as metal is a good conductor of heat and the expansion of gas is very slow, heat will enter the metallic cylinder from its surroundings and keep the temperature of the gas constant. I repeat, so here we get the help of two things to keep the temperature constant. Factor one is metal, body of this is made up of metal. So metal is a good conductor of heat. So expansion of the gas is very slow. So two things. One is the conductive material, and the second point, it helps to keep the temperature constant, is that the process is slow. We have to process is slow, because even if the conductive material is present, if we do not give time, heat will not flow, because heat requires a specific amount of time to flow from one body to another. So we also have to give it an ample time so the temperature can remain constant. So two things or two favorable conditions should be supplied for an isothermal expansion. First one is the conductive material or rather isothermal process, not expansion or compression. Overall, as a whole, we can give two conducive points. One is the conductive material and another one, the process should be very slow. Now, for isothermal compression, what happens here? I have to move the piston downwards. I am moving the piston downwards. That means externally I am trying to compress the gas by applying a force on the piston. Now, as the compression of the piston of the gas is very slow, heat evolved. Now here heat will be evolved because when I am applying pressure on the piston is moving downwards, hence the temperature of the gas will rise. So there is an increase in the increase in the temperature as heat is being evolved. Now, as the compression of the gas is very slow, heat evolved will be transmitted to the surroundings through that conducting cylinder. In the first case, we had seen that heat is going to be absorbed because temperature is falling. As the temperature was falling, we had to supply heat from outside to inside so that the temperature can remain constant. Here what happens? There is an increase in the heat content, so heat is going to be relaxed or released to the surroundings. Slow process, conducive material, that is the conductive material, metal. So heat will be transmitted to the surroundings to keep the temperature constant again. Such things are known as isothermal compression. Now for a gas, if temperature remains constant, what happens? If temperature remains constant, the internal energy also remains constant. Internal energy also remains constant. Now we had seen that UF minus UI, there will be no change. Constant means there will be no change. Therefore, UF is equal to UI. The final and initial internal energies are the same. Then from the first law, we can say that Q was equal to UF minus UI plus W. Now this part is going to be 0 as stated here. This part is going to be 0. So Q is equal to W. That means, what does the statement mean? Q is equal to W. That means heat taken from the surroundings is equal to the external work done. Heat taken from the surroundings, Q, is equal to the external work done. Now for an isothermal compression, both Q and W are negative. This means that work is done on the system by the surroundings and the system loses an equal amount of heat. I repeat the statement. Q and W, they are negative for isothermal compression, mind you, not for expansion, only for compression. This means that work is done on the system by its surroundings and the system loses an equal amount of heat. So I have written the sentence for you. For isothermal compression, both Q and W are negative. This means work is done on the system by its surroundings and system loses equal amount of heat. Now, isothermal process of an ideal gas on a PV diagram. I discussed about this type of a diagram, P versus V diagram for such processes. Now, for a PV diagram, first we have to understand that PV is equal to RT. You all know this relation, that is the universal gas law. Now, for isothermal case, T is equal to constant. T is equal to constant for which case? Isothermal case. So now PV is equal to T, as R is constant, so you can write PV is equal to PV is equal to T, no, PV is equal to constant, because R is a constant and T is also a constant, so you can say that PV is equal to one constant value. Now this equation is represented by a rectangular hyperbola, as we see that this is P in this direction of y-axis, which is V in direction of x-axis. We get this as rectangular hyperbola. Now this is a temperature T1, temperature T2, temperature T3. Now T3 greater than T2 greater than T1. I repeat, these are in the shape of rectangular hyperbola. Rectangular hyperbola. Shape of rectangular hyperbola.